So here we found the rate constant. We know we want to find units for the rate constant. Well, one way to get the units is, we know this is a first order reaction, right? How would we write the differential rate law for a first order reaction? Going back to concentrations, what would the rate expression look like?
Rate equals K A to the 1. Or, oh, N to the 1.
Yeah, this is how we would use our old rate expressions that relate the rate and the concentration. So by the way, you need to realize anytime you know that something's first order, you could use either this or this as the rate expression depending on what the needs of the problem are. And we know what we would plug in for K, 0.00693. And we can now use our old methods to find what the units would be. But why don't we just find the units from this equation? So here's how we can find the units from the integrated rate expression. Here's something we haven't mentioned before. Logs always have no units. And if you raise something to a power, e to a power, that also has no units. Logs have no units, and you can't add things unless they have the same units. And you can't subtract things unless they have the same units. You can't do 5 apples plus 3 oranges. You can only do 5 apples plus 5 apples plus 3 apples.
Does K have no units?
So let's see. What are the units on this? No units. That means that this has to have no units. But time does have units. What are the units for time?
Seconds.
So what do the units for K have to be so that the product has no units?
Negatives? Oh, 1 over?
Seconds?
Yeah. Wouldn't these 2 units cancel and give us no units? All right, and then this could have no units, and add to this that has no units, that gives us this, which has no units. So that would be a simpler way to find the units. So what did we decide are the units for K here?
1 over seconds.
Yeah, 1 over seconds. Okay, if you feel more comfortable, you could have figured out the units from the differential rate expression, but for me it's easier just to look at this and see these have to have, the product here has to have no units to combine with this. Well, that means the K units have to cancel out the time units. So you have to cancel out seconds with 1 over seconds. Now, what types of questions can we answer? Well, for example, I could ask you, what is going to be the concentration of A, of N2O5? Let's see, they took this experiment up to how long? Oops. 400 seconds? So we could ask about, say, 500 seconds. Or we'll just stick with the example so we can check our work. Let's see, did we get the same answer as them? Yeah, good. So let's do, say, 150 seconds. All right, first of all, you could use this rate expression now. You could figure out what the rate would be when this concentration was, say, I don't know, 0.02. You can just plug in 0.02 into this and figure out this rate expression. But let's stick with the new time rate expression. Let's do a time of 150 seconds. It looks like we're going to have to go over a little bit more algebra. Let's say that you have that the natural log of x equals y. What would be another way of writing this?
Y, no, e to the y equals x.
Okay, good. Notice that the nice thing about that is it gets x by itself and gets rid of the natural log. Okay, so how can we figure out how much N2O5 we would have after 150 seconds?
Just plug it in to the equation.
Okay, so let's do that. That's the whole purpose of rate expressions. So let's answer those questions. So I'll plug in -0.0693 0.00693. What should I plug in for t?
150.
Right. And this is, and we've already figured out the y-intercept. So let's use our calculator. What number do we get there? Negative 3.3415. Natural log of n205 equals negative 3.3415. Good. But this isn't the answer, as I think you noticed, because this just gives us the natural log. How can we get this by itself? How can we rewrite this?
E to the N205 concentration, well, to the negative.
E to this.
Yeah.
This is the exponent.
Well, to the N205 to knock out the.
Oh, one thing you could do is you could make both of these an exponent of e. That's right. Or we can just use what we'd already said to go straight from here to here. So using this pattern, we can rewrite this like this. All right, now we have to know how to do this on our calculator. Looks good.
Okay.
So you have an exponential function key. It's over the natural log key, right?
Yeah.
Okay, good. So if you hit second in the natural log key,
Oh.
is that what you did there?
Just the regular E and then.
Oh, you also have a regular e as well. That's someplace else over the division key. So you can actually do it either way here. Okay. But since easier for me to use the natural log key, because that's what we were using. So second natural log, what did you get now?
0.03538.
What would be the units on that?
Molar.
Oh, molarity.
Because it's a concentration. Okay, all right. So now we know how to figure out rate expressions, and now we know what the rate expression is good for, because it lets you figure out a time that wasn't given to you in the table. So we had to do a lot of work here, right? First of all, we had to put all of these into lists. We had to see who was linear. Then, even once we knew this was first order, we still had to do work. We had to find what the y-intercept was. That was pretty easy. We had to find this using the slope. So we had to use rise over run to find the slope. But remember, we didn't just use a to find the slope. We took the natural log of a. So you got to be careful with that, because that's what the equation is. Notice how I keep asking you, what's the vertical variable? That's what you have to keep focused on. That's what that table lays out, what the vertical variable is. Only once we have all our constants can we use this to answer new questions. Now we plugged in the time. And we have to do algebra there as well to get rid of that natural log. Any sense?
Mm-hmm.
Okay, well, we should try to do one more example of this.